particularly well yesterday. So today, everybody, we're going to start on the process of looking at section 1.2 of our textbook, which doesn't mean much to you, but I can tell you 1.2 is the building blocks for all of math analysis. We're going to start learning anything and everything there is to learn about functions, okay? So what I wanted to start with is what makes a function. Now I do know that many of you probably are aware of this in a sense. And I'm going to go ahead and take this off and go back to my shield because I think my voice carries a little bit better if I'm this way than that. But do you guys remember what makes something a function? Something that passes, there's a certain test. Yeah, it says you can't draw that vertical line in, and what if you drew that vertical line, what's supposed to happen? It's only supposed to, what if it never hits at all? Would that be okay? Yeah, that's okay too. So what happens is a function technically is a relation. Now that's really strange. It almost feels like circular logic to define it that way, but it's a relation. See, there are some relationships between numbers that are actually not functions, and that's okay. So a function is some kind of a relationship between two numbers in which every member of the domain. Now, do you guys remember which letter in there is the domain usually? It's usually X. I'm going to put, that's the input or X, right? Every member of the domain, that's the input or the X value, which we often will also call the independent variable. Each of that independent input or X domain maps uniquely to a member of the range. So uniquely means when I do it, I can't get two answers. And the range is usually the output. Some people will call it the dependent variable. Usually you guys probably prefer to just call it flat out Y. Does that make sense? So it means for every X, there's only one. Now this term map, when you go into more advanced mathematics, a lot of times they like to do things like this. So let's imagine I have this story right here. And I have, this is my domain. So what are all the inputs? So is that legitimate that I could have that? 1, 2, 3, 4, 5. I could make a story out of that. I have a situation where I have some jobs to do and you could choose to be hired for 1 hour, 2 hours, 3 hours, 4 hours, or 5 hours. You're like, well, what about if I want to work for 8? Go find another job. That's what I'm offering. Can I do that? And so those are the only things that you could do. And then over here is my range. Have you guys ever seen bubble maps that look like this, where you can just literally just do kind of a mapping correspondence? And I gotta say, this doesn't too much matter. But you have something like this where, and I'm kind of making it purposely weird for you. And okay, now the question that I have for you is, in my definition of a function, does this match? Does this fit? If I ask you the question, hey, I gave you 2, what's the output? 8. Is there only one output that you get when I say 2? That's it, right? How about if I said 5? 6. How about if I said 1? Is that a problem? No, that's technically still a function. This is a function because what it says is if I give you a member of this, you have a definitive answer that when you go over to here. Now, what I love as an example of that is, imagine that we had a soda machine, and if you had me for Algebra 2, you may have heard this exact same analogy, but it just works. I like it because it just works. If there was a soda machine out there and you had all these buttons, think about it. Would it be acceptable if you had a machine out there and the first 3 buttons all gave you water? Is there something wrong with the machine if the first 3 buttons give you water? Some of you be like, I don't like that machine. Why am I paying for water? Well, you know that's what it offers. It offers water if you hit those first 3 buttons. How about if the 4th button is a Dr. Pepper? And you go down the line. What's not a good machine is if the first button gives you water one day and then the same button the next day gives you what? Something else. I mean, it doesn't matter. Oh, I hit the button today, it was water, tomorrow was milk. I'm like, oh, milk is nasty. That's terrible. It has to be predictable. Now, this is the example that is the bad example. There's, in a sense, it's fine. I've got this domain going like this. I've got this domain. I've got that range over here. And I've got something like that. No big deal. We go along like this, and we're like, okay, well, 1 gives me 5. 3 gives me 6. 4 gives me 6. 2 gives me 5. 2 gives me 6. See, if I press the 1 button, is there a problem? I know it's well behaved, it's gonna give me 5. Where does the problem arise? Because the fact that for one singular input, there's multiple potential outputs. Now, think about that from the state of what happens in your vehicle. You have something that is an input, which is called a brake, right? What should happen when you hit the brake? That's your input. Your output is you slow down or you stop. What if we changed your vehicle and sometimes when you hit the brake, it slowed you down and other times it turned your radio on? You probably would stop liking, you wouldn't really know what's going to happen with that. Or you hit the brake and it calls your mom, like through the system. You want things to be predictable. Now, would it be okay with you guys? Think about this. Would it be okay with you if you had a vehicle that had more than one way to turn up the volume on the radio? Is there something wrong with a vehicle that has multiple ways to get something done? No. See right here? If my goal is to turn up the radio, how could I make that happen? Tell me one. No, no, seriously. In real life, how do you turn up the radio? Turn the knob. Is that the only way to turn up a radio? What's another way? Steering wheel. Boom, boom, boom. Does anybody else have it hooked to their phone and they could just slide it on their phone and adjust the volume on their phone? Is that a problem that you have multiple ways to get this happening? That is not a problem. This one right here, though, is. That's kind of what I wanted to encourage you to understand. Now, what we often will hear is this idea of the vertical line test. So when we look at a graph like this, is that a function? This is a function. This one is going to be kind of weird, and you might look at me like, Penner, that's bizarre. This does not exist in the real world. I would actually argue that you are wrong. Is that a function? Now, it's kind of bizarre, but if I draw a vertical line, how many times did it hit? Just once, but what happens when I slide it right here? It still hits once. It missed the bottom one, but it picked it up on the top one. It's still a function. These are functions, whereas the classic version like this right here, which is actually something we are going to study a fair bit this year, that is the graph of x equals y squared, incidentally. That's not just something that I made up at random. That's x equals y squared. What's the problem with that one? Notice that it fails that vertical line test. We know that there would be an issue. This is not a function because we have an issue with it. I don't think that is particularly hard or crazy. Now, that is a visual way of looking at functions, but what I wanted to look at today, and this is really the basis of the biggest part of my lesson, is finding the domain. So in the first example, was the domain easy? You look up here, and the domain of this problem is 1, 2, 3, 4, and 5. What's the domain of this one? It would just be 1, 2, 3, and 4. I think the domain of this one would probably be implied as all reals because I have arrows. It's just going in all directions, right? Same as here. What about the domain of this one? What values of x did I use in this particular, not function, but this relation? Not just positives. I think I picked up 0 itself. So like this one would have a domain of x is greater than or equal to 0, right? So from a graph, it's fairly trivial. But what about when we start looking at equations? So I'm going to go through a series of equations right here. This is your standard polynomial equation. What's that a graph of? What shape did I just get? A nice little parabola, correct? Everybody cool with that? So the question that I ask you is, just analytically, what can I plug in for x? Could I plug in 0? Absolutely. Could I plug in 185? Could I plug in -10? You're not going to like this, but could I plug in the square root of 3? Is there anything I cannot plug in? Is there any restriction to say, hey, whatever you do, don't plug in this thing because something bad's going to happen? The domain of this is all real numbers. Now, you could write out those two words, all real numbers, but the faster way to do that is to write that. It's a capital bar, R, and that's shorthand in math to say what? All real numbers, because nothing bad can happen in that problem because everything is defined. So g of x is going to be a little harder. Instead of giving you a polynomial, which is all reals, I wanted to give you this guy right here. This is called a rational equation. Now, something bad happens this time. This does not have a domain of all reals. Anybody know what x cannot be? X cannot be -3. Now, why can x not be -3 is because the one thing in math you can never, ever, ever do is divide by 0. It makes no sense. It violates the definition of division if you try to do it. Bad things happen. So my domain here, quite simply, is I'm going to write that. Now, that seems kind of trivial and simple, doesn't it? But I'm saying, hey, don't pick -3. What am I telling you can pick then? By saying don't do this, what am I saying you can do? Anything else. So can you guys answer then a similar problem to that right here? Your h of x is going to be 7x over x minus 4, 3x plus 7. So what would be the domain of that rational equation? What can I allow x to be? Very simple. What are the bad things that happen? Nico, tell me something that's bad in that problem. What would make the denominator here go to 0? 4. Don't pick 4, whatever you do. That's exactly right. Frankie, what about here? You can just kind of look at it and see it. Can anybody help us out? Don't pick -7 over 3. So what can I pick? I can pick anything that I want, except I can't pick those. Now, if you were going to actually go ahead and go into our good old friend Desmos, which I'm going to try to do. I'm going to share this so I can get over here to a Desmos screen. I want you to see visually what happens if we try to look at that. So I gave you a simple equation, which was 7x divided by x minus 4 and 3x plus 7. Now, if you look over here, that's a crazy looking graph, isn't it? And if I go over here, let me go ahead and let's go ahead and add a table. And I don't know if you knew that you could do this, but I could put x here And I could, instead of putting that, I could put h of x here, and I could say, could I ask the question, hey, calculator, what happens at 3? Will it get, oh, you can't see that. Sorry about that. Let's see if I move that down, if it'll show up on your screen. Okay, so can I ask a question about, say, 3? Notice that it showed up over here on my screen. Could I ask a question at 3.8? What happens if I tried 3.99? I'm allowed, oops, 3.9? Do you see how it's there? Oh, that's funny. Desmos is having trouble. What happens is it gets really, really close to the number 4. Where is it going? Do you notice anything? At 3.9, it was at about negative 15. Now it's at negative 147. Where's the thing going? It's going down. How fast? Really fast. That's called an asymptote. See, because what happens if I say, hey, calculator, screw it. What happens at 4? What does it say? You cannot do that. So I can ask any question in this thing, and it would give me an answer. Now, why can't I ask the question at 4? It's because what is x equals 4? You guys remember what we called that last year? I know you studied this. I know you did. It was a vertical, yes. It's called an asymptote. It's something you're going to get infinitely close to, but you're never going to quite touch that asymptote. See, because what happens is you try to get close to 4 from the right side. Where does the graph go? It goes up to infinity. As you try to get close to 4 on the other side, what does it do? It goes down to infinity. So, but you can't plug in 4 itself, right? You guys cool with that? So let's go ahead and get back to here. All right, so your turn to try number 4 all the way, and I'm not going to rig this one. Yours is j of x. Now, notationally, you guys are probably used to f of x, but I use g of x, I use h of x, I use k of x. It's kind of like, you guys know who George Foreman is? You guys don't know who George Foreman is. George Foreman is an old famous boxer. He was a really, really, really big dude. So he was this huge guy, but by the way, he was also a reverend. So he was a boxer. So what does that tell you? Could he fight? Honestly, he actually won the heavyweight title. Could he fight? Oh, he could tear people up, but he was actually a nice guy, which is kind of ironic because he was actually a minister, and he has lots and lots of kids, like 7 or 8 kids. And guess what their names are? George. Every one of them named George. See, that kind of sucks because it works for when you're calling kids for dinner, but if somebody broke something, you yell George and everybody runs for cover, right? It would be a bad thing. So when I name functions, I don't call everybody Fred or everybody George. I give everybody a different name so we know what equation. So this is just different names. But I want you to find out where is my domain here. And if you haven't caught that I want you guys to be able to factor, you're missing my message. I didn't factor it for you. I want you to factor that and tell me what values of x I can have and what values of x I cannot have. And factoring is going to be our key to that particular problem. Was anybody able to come up with my 2 factors? 3x and x. Is 4 going to be a 4 and a 1 or a 2 and a 2? It's going to be a 4 and a 1. Do I want to put the 4 in the first gap or the second gap because I'm looking for an 11. Second gap. There we go. 12 and a 1 makes 11 if the 1 is negative and the 4 is positive. Okay, now we've got it. So guys, what are the two bad guys? What are the two things that I have to say, hey, you know what, don't pick this? What are the two bad things that I cannot have? I cannot have -4. -4 would be all bad. And what else would be bad? Is it -1/3? No, it's +1/3. Yeah. Now, could you validate that by graphing it and making sure? What do you think would happen at -4 and +1/3? If you remember what my graph looked like a moment ago, what should show up at both of those things? It should just bank away. There should be asymptotes in that thing, right? So far, are you doing okay with that? Okay. Now, I'm going to go ahead and mess with your brains just a little bit. Number 5. Here we go. We're going to make something that's a little bit different. My new one, we're going to go with k of x. I don't think I've used that yet. This is going to screw with you a little bit, but I'm trying to make the problem easy, but the concept a little more advanced. Does this look very different than the previous question? It's just a nice little line over a quadratic. It's a line over a quadratic. So step number 1, let's factor that thing. Now, I did that on purpose. You guys see that? I did that on purpose. So what do you guys think are the two values of x that you would say, hey, everybody, don't do this thing? Don't do -4. And don't do, would you guys buy that? But does something jump out at you that looks so weird about this particular story? Does anything jump out at you at all? The x, does that seem strange that you have an x plus 4 on the top and bottom? What should happen if you have the same thing on the top and the same thing on the bottom? They should cancel out, shouldn't they? Now, here's the deal. Why do they cancel? What does it mean when you cancel out? Plug in the number 2 in your head. What's the top say now? 6. What does the bottom say now? And they canceled out, don't they? So in other words, what do these add to the problem? Is they add nothing because 6 over 6 would be 1. That would just disappear, right? What about if you plugged in 9? Still 13 over 13, and they cancel out. But what happens when you try -4? You get 0 over 0, don't you? Is 0 divided by 0 1? No, it's not. But that actually leads you to something that's actually really, really super significant, because watch what happens in this story that you may not have realized that happens. I got x plus 4 on top. I got x plus 4, and I've got x plus 1 in the bottom. And in the other problems, we had 2 vertical asymptotes. And what I want you to see in this one, how many vertical asymptotes do you see this time? I see 1. Do you even see a problem at -4? See right here? Right in here. Is there even a problem? Do you see something wrong at -4? Do you see it? Because I don't see any remnant on my equation that anything is wrong. In fact, if I tried -3.99999, I'm getting it super duper close to -4. Is anything going wrong? But what happens if I actually say, hey, calculator, what happens at -4? What does it say? So I can get infinitely close to it, but I can't touch it. Do you guys know what happened to the graph? Okay, well, this calculator has the ability to show something that Desmos doesn't. And it's honestly, it's kind of funny because this thing has bad graphics. It actually helps, and I'll show you how. This equation was x plus 4 divided by x squared plus 5x plus 4. And we just said that the problem happened at specifically -4. Now, I know that you might be a little bit unsure why I'm picking the window that I'm picking, but because the problem happened at -4, I made -4 right in the middle of 0 and -8. Okay, and I just know on my calculator functions. And watch what happens. Oh, you bugger. -5 to 5, 0. Oh, because it should be -8 and 0. Sorry about that. Okay, here we go. Do you guys see anything? Do you see the little point that's missing there? You see right there, there is a hole. So how big is the error in this problem? It's infinitely small, isn't it? Like, you would not know it's there. Now, in reality, how big is a point, everybody? How big is a point? It's infinitely small. In Desmos, why didn't you see it? Because it was infinitely small. In this calculator, though, what my calculator does is it is programmed. If you look carefully, there's these little boxes on it. It's programmed to plug in all those little boxes and then play connect the dots. That's how it's programmed. Well, guess where one of the dots is every single time? Right in the middle. So if I make my error happen smack dab in the middle, I'm going to see that missing point if it is there, which leads me to our next little piece. So this thing is called a removable discontinuity. So in my list of things today that we're going to discuss, we're going to talk about domain. We're not going to talk about range that much, but we're going to talk about domain a little bit. We're going to talk about continuity. Is this graph continuous? Like it moves along and it never has any breaks? No. This one has a removable discontinuity here, and it has an infinite discontinuity here. Now, why did I say it has an infinite discontinuity? What did the graph look like at -1? Was that thing that had that vertical asymptote, right? So is there a break there? Was there a break at -1? Yeah, but it was not just a little break. How big was the break? Look at it. How big was the break at -1? You see it? One side went to positive infinity, one went to negative. It's not a little teeny gap. You can't just make a little bridge and fix it, can you? It's infinitely large. So we have two different kinds of discontinuities so far. One of them is called a removable. Now, why would we call it removable? How big was it? Infinitely small. Could you have repaired it if you had a patch kit? Yeah, you could. Just a little bit of dab of something and that would fill in that teeny little hole, right? So hopefully you got this. When will you get a removable discontinuity? What has to happen to make that occur? You have a perfect common factor top and bottom. Please notice I did not cross these out. You notice that? Why didn't I cross them out is because if I crossed them out, then I would believe that 0 divided by 0 didn't matter anymore. If I crossed them out, I would change the domain. Okay? All right, number 6. Got one more thing to talk about in terms of domain, and this is a little bit tougher for you guys, but I'm going to go ahead and give you r of x is the square root. Now, I'm going to go ahead and do 4 plus x. I'm trying to make the notes as short as I can because we have to cut that half an hour out every time. What am I worried about in addition to never, ever, ever dividing by 0? What else might I be worried about? Rooting negatives, okay? Now, is that by definition then saying this is an inequality? Because you're saying take a root, but what roots do you want? As I want the root of 0 and I want the root of positives, but I don't want any negatives. So what I would love to see you do is pop it on a number line. Super easy to do. -4 and 3. Now, there's a fallacy that I keep hearing from students over the years that I can't take the square root of 0. Yes, you can. What can you not do? The root of a negative. So let me ask you a question. Give me a number above 3. Any number that you want. 6. If I plugged in 6, what is this entity right here? 4 plus 6 is positive. I don't care that it's 10, it's positive. What happens if I plug in 6 right here? 3 minus 6 is, well, 3 minus 6 is negative. Can I do that? Can I take the square root of a positive times a negative? No, don't do that. How about inside here? What happens if you're in here? This is why we did the sign graph method yesterday. What happens inside? 0 would give me a positive and a positive. Am I allowed to do that? Absolutely. Can I go out here? What happens if I go way to the left and I try something like negative 10? What's this one? 4 minus 10. Negative. What happens if I try negative 10? 3 minus negative 10. Oh, it's positive 13. Can I do that? So according to this, the domain of this graph is that we only have values from negative 4 to 3. So what can I pick? Could I pick 7 as an answer to plug in? No, because I rooted negative. I can't plug in negative 8 either. You guys may not even know what this thing looks like, but it's kind of worth showing you. What the heck does that actually behave like? We know what its domain is. It had 4 plus x, right? 4 plus x. 3 minus x. What? What did I just make? What? It's a semicircle. Believe it or not, the square root of a parabola is like a semicircle. That's weird, isn't it? And so notice, I can ask all sorts of questions. You see it? I can ask all of these questions, but what happens when I pass the number 3? What's going to happen? All of a sudden, the calculator says, nah, you can't do that. Why? Because what would happen? It would be impossible because I'd be taking the square root of what? Negative numbers, okay. So, for you guys, the 2 things that I do not ever, ever, ever want to see you do is divide by 0 or what? Root what? Negative. So, for the next couple of weeks, if not better than a month, anytime that I ask you a domain question, what are the 2 things you're going to guard against? Dividing by 0 and taking roots of negatives. Okay, so your turn to try number 7. Okay, so let's see if you guys can figure out then what this one is. This is a hard concept for a lot of people. So understand, if you're struggling with it, I get it. I really do. So this particular problem, I'm throwing everything but the kitchen sink at you. Is it possible that you could take a square root of a negative if you picked a bad x in this one? Could I make this x big enough that it would go over the top? Could I make this x bad to where it would make it blow up? Like if I tried 0, what's 0 minus 6? Oh, that's a problem. Is it possible that I could divide by 0? Okay, I'm going to give you a second. I want you to think about it. Make a number line, and I want you to think about what values should go on your number line. Okay, what would make the bottom go to 0? Root 6. What happens if I plugged in root 6 and then I squared it? And then I subtracted 6. What would I get in the bottom? Wouldn't I get 0? Can I do that? So why am I going to put an open circle there? Because I can't touch it, right? Because what would happen if I did touch it? I'd be dividing by 0. Is there any other number I should put on that? Ooh. What happens if I tried negative root 6 and then I squared that? Would it also make the bottom go to 0? Yes, well, I better not do that either. Okay, so I know, so have you considered division by 0 as a bad guy right now? So check that box. Divide by 0. We checked that. We looked for that. What else are we worried about in addition to dividing by 0? Is we don't want to take the square root of negative. We'll watch what happens. What happens if I go above root 6? You guys tell me. Give me something that's higher than root 6. 6. If you plugged in 6, you get 7 on top. Is that okay? By the way, the top is always okay. What happens if I plug in 6 in the bottom? The square root of 30, can I do that? Yeah. In fact, as long as I pass root 6, what's going to happen on the bottom is anything bigger than root 6 squared is going to be bigger than the 6, isn't it? And that's going to make it positive, and then life is good. What about out here? What about if I go below negative root 6, like negative 6? Will that also work? Because what happens in the middle? Anything below root 6, anywhere in there, what's going to happen? The bottom is all of a sudden going to become some number divided by the square root of a negative. And what's going to happen then? You can't have it. So this domain, everybody, is everything from negative infinity to negative root 6, and then again, everything from root 6 to infinity. And you probably don't know what that graph looks like, but by context, I think I have a little bit of an idea. So I think it's probably worthwhile to take a quick look at it. And let's see what Desmos shows that that actually looks like, because you had x plus 1 on top. Ooh, that's weird. Too much stuff. Make all that go away. You had x plus 1 on top. And you had, now this is something kind of weird. Do you guys remember what the square root of x squared was? We said it was an absolute value, didn't it? This is kind of strange. There's a reason why this actually works. Oops, that was supposed to be squared. Minus 6, and I need to put a square root in front of this. Oh, fail. Go away. Ooh. See? Do you see how I can ask questions out here to this side and this side, but what happened in the middle? There's nothing there. That graph flat out does not exist anywhere in the middle. Why? Because the domain says you can only pick values on the outside, and those are the only legit values. So as far as what I have assigned for you, and this is like the last time I'm seeing you guys actually for until next Monday, correct? So it's going to be a little while then. So what you guys have on tap for the next little while, let me go back to the computer, is you guys in Google Classroom, in chapter 1, what I would like you guys to do, let me see if I could find it. Here it is. This is the assignments for chapter 1. What I would like you guys to work on is 1.1. Now it's called regression analysis, and regression analysis literally means what you're going to do is you're going to try to take data and try to see if you can model that data as an equation. People do that in science. Did you guys know that they're trying to figure out how will the coronavirus spread? How do they do that? Well, they look at data, and what do they try to do with that data? They try to match it to an equation, and if they have an equation, could they then plug in new numbers like in the future and see what they think should happen if things continue on as they are? That's mathematical modeling. That's what we're doing in those first 10, is taking a look at data and trying to come up with equations and match them together. Now in this 1.2a, every year I have some students get confused. They're like, I didn't find a 1.2a section. It's section 1.2. We're just going to spend more than one day on it. Okay, so within that section, you're going to do, sorry, I changed the assignment at one point in time. So it's really 1 through 16 all. I don't frequently give you alls, but in this particular case, you'll see why I did when you get into there. And you're going to notice and you're going to pop around to some of these others and go through it. Now, my plan is on Monday to go back through some of the pieces of this, because as you go through this list, have we talked about domain and range? At least a little bit, but there's a lot of stuff down in here we haven't discussed. So when you get to something that you're like, wow, we haven't really talked about it, you would be able to pause on those questions because we're going to resume next time. I didn't get to all of it, but honestly, what does a maximum sound like? Doesn't sound like a high spot. It's not that hard. Where does a minimum? Like the low spot. So, you know, there's some things that you could probably understand just because you're a human being and understand language a little bit. And even though we haven't physically talked about them, you could probably do that. So that's where we are stopping for today. And so even though you do not have me for the next little while, you may still feel free to communicate. Please ask questions back and forth. If you did not turn in your homework, fix that as soon as possible, okay? For those of you guys at home, I would like to see you turn in those assignments virtually through Google Classroom. So today we turned in specifically prerequisite number 3. Some of you have already done that. We turned in systems of equations, row reduced echelon form, and I should probably just share that this way so you can see what I'm talking about. So prerequisites number 3 worksheet on quadratics, systems of equations, the one that said homework, row reduced, which was the idea of dealing with matrices, and this one was the challenge questions that we worked on in class where I put stamps on them for people that did well, and I did post a video of how I came up with all my answers for those online. So if you go into the Google Classroom stream, you will see a video of my solutions of all of these. So if you have any issues with how to solve those, you can look those up. So anyway, I'm going to go ahead and sign out now. It was good being with you guys. You've all had your mics off, which I do appreciate, but I'd love it if you'd interact some too. So have a great day, everybody, and I will see you soon.